So the context here is that we all struggled during the pandemic, professionally as well as socially. Today is the time where we can sort of now we have had enough buffers where we can recall some stories from the pandemic, stories of science, technology, and innovation. But these stories are not just limited to IISc, but it goes beyond. In this morning session, we'll look at what has happened at IISc, innovation from IISc during this period, and in the afternoon session is dedicated to maker spaces outside IISc and about their journey. So in the wake up of COVID-19, people from different walks of life came together to fight the pressing global issues posed by the pandemic. Individuals and institutions across the country demonstrated an inspiring innovation spirit. Several science and technology-based innovations and inventions were developed to combat the devastating virus and the societal challenges it brought. IISc is a premier institute in India known for its excellence in scientific research, and it leveraged its intellectual capability to aid pandemic management across various areas, some of which I'll very briefly list out. So for example, development of diagnostic tools and therapeutic kits for COVID-19, development of biomedical devices to aid the management of COVID-19 patients, development of preventive kits and tools, including disinfectants and sanitizers, and of course, development of several algorithms, simulations, apps for tracking the spread of the virus, virtual record keeping, symptoms check, and so on. The research and innovation that happened at the academic level were complemented by the contributions from the civil society organizations towards this cause. In particular, makerspaces played a key role, especially helping with addressing the shortage of face masks, face shields, PPEs, and by repurposing existing facilities and equipment for increased production to meet the surging demand. So this event is organized to provide a platform for academics at IISc and people from makerspaces to showcase the innovative solutions and technologies developed during COVID and talk about the impact in pandemic management. As an overarching goal, the event is also interested in looking at broader policy and regulatory challenges that innovators face. In particular, we want to identify the gaps in policies required to promote innovations and inventions from institutions and universities in India. And of course, and in addition, assess the impact of open innovation and implications of restrictive IP strategies. Right. So with that, I'll invite our first speaker, Professor Rahul Roy, who is an associate professor of chemical engineering and an associate faculty at the Center for Biosystems Science and Engineering at IISc. Professor Roy has done his BTech in biotechnology and biochemical engineering from IIT Kharagpur and completed his PhD in biophysics and computational biology from the University of Illinois, Urbana-Champaign. One of the primary challenges during the initial days of COVID was how to detect the infection. Professor Roy and his team have developed two distinct variants of indirect ELISA tests to detect SARS CoV2 specific antibodies. We'll hear from him about the details. So please welcome.
Do you want me to plug this in, or would you like to? I have a copy.
Yeah, we'll take a couple of minutes while we get the USB sticks and start from there.
Without that, otherwise,
yeah, because if I have the link, I can log in. That might be easier because I'm trying to remember where the link is. She has already. Do you have a flash drive with you? I think the one I copied into, I forgot. Imagine.
The Zoom link. I think
Hmm?
he has sent it to me. You can take this out. And I'll go.
Mr. Sanjeev, volume is not here. I think we will need the Zoom mic.
Mute the mic. Mute the mic.
He has muted the mic.
You tell him to just,
Why?
I told him, because he muted the mic of the Zoom mic. You see, he can,
Yeah.
he has muted the mic.
Did I ask to unmute?
Yeah, I should ask him to unmute the mic, then the volume. Still,
Mhm.
Sorry, my bad, but this will echo. So I will stand as far as possible from this and hopefully it'll be fine. All right, so, and the reason we decided to do this, because this is an assay that's commonly used in the clinics. It is commonly used in almost for all kinds of studies which are research-based trying to detect antibodies. The reason we started doing it, and we had no experience in doing this, the reason we started doing this was because we were finding reports again and again which were telling us that if the quality of whatever was being built in the country was just extremely poor. Okay, so import licenses were cancelled by CMR, suspended because they just did not match the quality standards that were required. Okay, so at that time, there were some studies that told us that yes, you could detect, but the sensitivity of those tests were also poor. You could only detect 75% of the time, or 80% of the time, 85% of the time. Commercial ones like this were doing extremely poorly. Okay, this is made by ICMR itself. Okay, and if you want to talk about it, I'll tell you more about this. But the point is, even if you bought it from outside the country, so this is a commercial test available at that time from outside the country, the sensitivities were quite poor. So within 10 days, only 30% of the cases were detected. And even after, only after 3 weeks, you could detect 94% of the cases. So it was taking too much time. And I said, this is ridiculous. This is a simple enough technology. And I'll show you quickly how simple this is, that people are not able to do this. Of course, when you start doing something, then you realize there are always challenges to everything. But the point was, at that time, we thought, yes, even if we are engineers, we should be able to do this. So this is what the tests look like. Normally, what you have is in a well, some buffer, but more importantly, the molecule of interest is called an antigen. This is a part of some part of the virus, which is attached to the bottom of the well. And then if your body has produced antibodies against it, in the blood, you can detect them, or in your sera, you can take the sera and add it. If it is specific to this particular virus molecule, then it will go and bind, and their affinities are very high. So they will stay there. You can wash away everything else, and then you can put a secondary antibody which detects this particular molecule. Right? So this will tell you by some kind of a calorimetric titration, you can figure out whether you have got any of these molecules. And this is usually linearly proportional, but of course, there's non-linearity at the extremities. So that's what the challenges are, okay? We also were able to very quickly go to Bangalore Medical College and approach Translational Health Science Research Institute in Faridabad. They were already building a repository, biorepository of these kinds of positive samples, thanks to DBT funding. And they were able to provide us samples, so we could take the large number of samples, validate this both on the positive samples, but also on negative samples. And we had a bank of old samples with us because of some previous studies that we had done. So we could take advantage of the fact that there were pre-COVID and hence we could use them. We also, I was telling somebody that we work on infections which are quite prevalent. So all these samples are already very, very positive for infections that you already hear a lot. Okay, but negative for completely negative for COVID didn't take this. All right, and then you do a lot of titrations. These are nothing but doing those tests again and again and again, automate as much as possible, and so that you can measure as quickly as possible, as many samples as possible. And these tells you, the point I'm trying to make is that once you make these, you can characterize and find the linear range over which you will get antibody levels and the signal to be corresponding to each other in a fashion. So that's basically why we are doing this exercise. And we test, of course, a lot of different antigens from the virus, this protein, that protein, this part of the protein. I'm not going to go into the detail. And then you compare them and you figure out that at least for one of the antigens, which was the total primer that kind of is responsible for binding, spike primer that is responsible for binding your cells, that seemed to give you the best sensitivity. So we had about 90% sensitivity and 96% sensitivity. And this 90% sensitivity would bother you. So you're not doing much better than what others were reporting already. And so we always found that there were antibodies not present, even though we knew that these guys had SARS CoV2, we knew that they were all tested positive, we would find that they did not have antibodies. So we still don't know the reasons for all of these individuals, but sometimes we found that not every time you would evoke a response, number one. The second was that many times the tests themselves were wrong. They were RT-PCR positive, but they were not actually SARS-CoV-2 positive. Okay. So when we compared our tests, so the other tests, whenever other tests would say positive, we were always 100%. So our tests were detecting antibodies completely 100%. Okay, to make this test, and then we say, of course, we can't scale it up ourselves. We had made it in such a way that we can quickly give it to a company. The companies already do these kinds of things all the time. They already have similar platforms. They just need to change in the whole pipeline. They just need to change this reagent. That's it. And everything else, we are telling them exactly how much to add, which ones to use, and so on and so forth. They already have prior experience. So they should be able to very quickly go and build this and be able to sell it. So NeoDX, we talked to lots of companies which did that. And many of these companies were importing antigens from outside the country and then trying to build this test on their own. And for various reasons, we couldn't convince everybody that they should be doing this. And that this was because they had advisors from US who were telling them, no, you should use the antigens from US and so on and so forth. So for various reasons, we couldn't. NeoDX came forward and licensed this. But we then ran into other issues. The test works. We have given it to our company. We have helped them kind of standardize it, that they make the test kits, and they send it across to ICMR for validations. And this is the time when kind of everything is in a flux. So ICMR is, for the lack of knowledge, is evaluating their protocols for validating these tests on a weekly or a bi-weekly basis. And then the effect of that was you would send them the test kits, and then you get an information from them. Oh, by the way, you need to send more test kits before we can kind of give you the certificate and so on and so forth. And by the time we went back and forth between ICMR and the company was doing this, of course, they realized that this was kind of a incremental gain in terms of what they could do very, very quickly, because they were also making these PCR tests, and they had already got permissions to kind of sell them, and they were selling it everywhere. So the amount of money that they were making out of it makes kind of sense for them to invest more people onto this. So as far as I know, this test is, we call it the Zero-CoV ID, is still on the back burner for these company. We, of course, didn't do an exclusive I'm still open to talking to other people. But if you are interested in details of this test, this is already in the public domain, so feel free to look it up. The innovation was very little in the sense that we did not invent anything new. We just characterized things that were already there in the public domain, and we kind of built this so that it could be as quickly as possible be in the market so that it can be used. Okay. There was a lot of utility. So, for example, while the commercial test was not available, we could very quickly go and look at people who were getting vaccinated. The same antibodies are generated when you get vaccinated, and those you can monitor using this test. So, for example, we have a cohort of people where we have looked at people who did not have COVID before and got vaccinated versus people who have had COVID before and then got vaccinated. And is there a difference in their immune response? And what we do is from the time of their vaccination, before their vaccination, to the time beyond up to 1 year, we have been collecting samples for them and measuring their antibodies. And you can track their levels of antibodies, which tells you the kind of immune response they are having. So some learnings from those are things like so the red ones are people who had virus infection before. So as soon as you give them vaccine, you see a huge jump in their antibody levels. Okay, so it is as if that the first one infection that you have had is acting to prime the immune system, and then the second one, the first kind of vaccine that you're giving them is acting as a booster for them. Okay, and they maintain these antibody levels for a long period. If you look at the naive people, of course, the booster is necessary to get them up to the same levels as you would otherwise. Okay. We also could now ask more complicated questions. How much time do you want to have as an interval between the two doses? What will give you the best antibody? And what it shows here is that a very nice linear correlation between how much antibody you get and how much spacing you have between the two doses. So all this we can now measure using the tests that we have. There's another example of something else we have done, and many other things, but I'll show you this one because you can also ask yourself whether you are really protected. And you have one measurement piece, which is the antibody levels, right? So we look at people who have had no vaccines, one vaccine dose or two vaccine doses, and then they're ending up in the hospital with a vaccine, with an infection, okay? And when we look at the people, this is not surprising. So people who are fully vaccinated or partially also vaccinated, they don't seem to have severe disease. But if you don't have vaccination, and this is not surprising, it's common sense, people who did not have any vaccines, they were almost 40% of those people were getting. But the more important thing is that our test would also tell you that. So here's people who had very mild symptoms or no symptoms. Those people had usually higher levels of antibodies, and people who had always low levels of antibodies, they were tending, at least the people who got severe disease, they always had lower antibody levels, according to the test. So that tells you that there is merit in using these kinds of tests in being able to predict whether you have a chance of having a severe disease. Okay, so you can develop these things, simple things, but you can very quickly make impact, and that was what our goal was. But while we were doing this, we realized that in spite of being simple enough that could be developed in a few months, we are not doing this. And we have a huge infectious disease burden, and we are not doing anything in a kind of a scientific evidence fashion. So I'm primarily interested in infectious diseases because I feel that we still have a huge burden that we are not addressing ourselves. Yes, of course, diabetes is important, but this is something that is curable. You just need to develop vaccines for it, right? And it's still in India, this is a major issue. So, and the problem is that lots of these infectious agents in the country are completely poorly. People come to you with a fever, and the doctor will immediately give you an antibiotic and just go. Even if it's a viral infection, they have no idea what it is, and they don't care. Most of the time, if I tell them, would you like to know whether you have this infection or that infection? And they say, what will I do with it? And most likely I'm going to give them a particular, because there are no antivirals in many cases. And then, of course, we don't know how prevalent these diseases are. That also information is kind of poor. So what we want to do going forward is that we want to be able to identify this pathogen prevalence and hope that once we know this information, how frequent are these infections, we can help health policy. The idea is to be able to build some kind of a ranked relative burden estimates for historical exposures to diseases. And we hope that that will help us prioritize vaccines, will help us kind of decide geographically where and how much priority should be given to, so defining kind of vaccine access and policies, antibiotics policies as well, and management of syndromic management of diseases. Okay, and I know for a fact with the kind of development we have seen that we can come up with fast vaccines thanks to COVID, and it is obvious. So once you recognize this, you can get to this much faster than it used to take before. So our hope is to do this, and thanks to the medical school kind of coming to the campus in the future, we have had lots of support for this. So we pitched a proposal to do this for not one pathogen like SARS CoV2, but for as many pathogens as possible across a very large cohort of people in the country. And this is something that the IISc Public Health Institute has agreed to support us with. So we call it MPATS, or multi-pathogen serology. That innovation is that you need a very small amount of blood, you collect it in some kind of a microfluidic paper device, and then this small amount of blood, which is usually from a pickup of blood, is sufficient to give you the answers for many, many different pathogens. And then once you have that, you can look not only for that particular pathogen, but also look for all kinds of factors, risk factors, demographic factors, correlations between diseases, and so on and so forth, and analyze that data. Okay, so the one major innovation is how to make this parallel. The way it works is instead of now attaching it to one single well, we are converting it into a bead-based assay. This bead, about 10 micron in size, would have antigen specific to a color-coded bead. This color basically will let you identify which antigen you are talking about, and the level of the antibody on this will tell you how much of this particular antibody you have in the sera. So in a single test, you will be able to identify how many different pathogens have it priorly infected and how much antibody levels do you have. Of course, we run these beads on a standard platform that already exists. So we don't want to invent everything, so that, again, adaptation is harder. So this is flow cytometry, where you have some kind of a bead going through a fluid profile where you will detect it, but these are commercial instruments that you can buy and then use it. And then the idea is that you can mix all the different antigens beads and then put them in the sera and then run in a single flow through. You can measure the antibodies against all the pathogens that you have put in the beads. Okay, of course, there's a lot of work involved. I won't take you through all of it, but the idea is to focus on Indian pathogens and Indian variants of those pathogens, not just standard pathogens, and some molecular biology, cell biology, developing these antigen protein engineering that takes you to this stage. So we are kind of developing this as we speak. And this is our current list of pathogens, about 17 or 8, sorry, my bad, about 18 or 19 viruses, bacteria, protozoa, and fungi, something that we have come up with this list, talking to hospitals, talking to doctors, and talking to public health experts. And our first version of this will be run in Karnataka, mostly around Bangalore and South Karnataka. So I'm happy to talk to you about. In a phased manner, we'll try to extend it to larger and larger areas. And I will stop here if you want to learn more about this, of course, I'm happy to tell you in the future. I also want to kind of acknowledge that this kind of work would not have been possible because of the way the science community, the general community kind of came forward. Okay, so of course, the students were holed up in their homes somewhere in outskirts of Bangalore. And when I told them, hey, I would like to do this, they immediately said, yes, I would like to come. They had nothing. They had never done these kinds of assays before themselves, sometimes never touched biological samples before. But they said, we would like to do it. I think it's doable. And then all I had to do was during the curfew, just go and pick them up in my car. Okay, and their parents, I thank their parents because they were worried about them, but they still let them go on those kinds of conditions. I also want to thank funding agencies and especially Capgemini India. So we got CSR support. We did not get, it was taking much longer. DST and DAGT, the ICMRs were overwhelmed. But Capgemini came forward thanks to efforts from the PSA's office. And they came forward and said, so Sapna Poti, I didn't put her name here. She kind of put us in touch with several CSR groups. And finally, Capgemini kind of funded this research. Of course, I got some money from IISc. I got some money from whoever it was willing to give us. We were happy to take it, and they did. We also got the reagents from several sources, as we can clearly say. Everybody just sent us an envelope, couriered us the envelope as soon as we asked them for the reagent. So I was amazed at the way science community was responding to this. There was a complete openness about sharing of ideas and sharing of reagents, and they got back things in return, in the sense that this antigen that we used in our test eventually is now part of a vaccine that is being developed in the US. And Jason kind of gave it to us for free, but when he got the data back from India, he kind of used that data to show that, yes, indeed, it is completely antigenic and would evoke a nice response. And of course, there was a large number of collaborators from all over the country. You will notice that not everybody is from Bangalore. They just pitched in whatever their expertise was. I would just write an email and they would immediately say, yes, I can do this for you. Okay, so I'll stop here. I'm happy to take questions. I'm sorry I went overboard a little bit. All right.
Right, I think we'll do the question maybe
Later? Okay.
Yeah.
All right.
We'll
So,
leave the laptop for a while and I'll
I'll leave it here?
Yeah.